Hi, Stats Kids. So I only have about 6 of you in class. I know you're all at home quarantined and probably freaking out about test 4, but don't freak out because we are going to do test 4. It's basically this study guide, and we're going to go through it together. So I sent you the blank study guide. I also sent you my completed study guide. And there's some other items you're going to need for us to do the study guide today. So you're going to need your Z chart. This is for chapter 8. You're going to need your T table. This is for chapter 8 and 9. And you're going to need this little handy dandy cheat sheet, right, that deals with chapter 9. So we're going to need all 3 of these items. So I have extras of these in class, but these are also on our Blackboard page, okay, under test 4 content. So you can find those there and print them out. If you can't find them, email me or text me, and then I will email you the attachments if that makes it a little easier for you. So just let me know whatever you need. Okay, so we're gonna start the study guide. Now remember, your tests, they're all multiple choice, so they are not going to look like this format. Yours are still multiple choice. It's just that the study guide that the department put out is 104 questions, and I don't think it's very good, so I'm not using it. So I made my own. So that's why it looks a little different than normal, because I just made this so that it resembled the test a little bit better. But yours is still going to be multiple choice, so don't panic. All right, so first question. What happens to the width of the confidence interval as the confidence level increases? Okay, well, remember these two are tied together perfectly. So if the confidence level's increasing, then the confidence interval is also going to increase. So it increases too. All right, so how are they related? Well, here's how they're related. When one increases, the other increases. Okay, now I'm just going to be lazy and leave it at that, but then the other thing you could write is that when one decreases, the other one decreases. So they happen together. They happen together. Okay, number 2, when making a confidence interval for the population mean using the T procedures, remember that's our T chart, the degrees of freedom for the T distribution are what? So remember, we have to find degrees of freedom. So what do degrees of freedom, what are they? They are n minus 1. So make sure you know that. That's how you find degrees of freedom, n minus 1. Okay, the next 2 questions deal with the T chart. And I've had some questions as far as how in the world do you read the T chart? Okay, so let's talk about our T chart. So T is still talking about, you know, what's going on under the curve, like Z, but it's a little different. Here on the left, you have degrees of freedom, which is just n minus 1. So that's how you find which row you're in. To find the column, you have to find the area under the curve in the right tail. So these guys are all areas, okay? That's what those are. All right, so here we go. The value for T, that's what it wants. So that's going to be something in the middle, one of these numbers in the middle. These are T values in the middle for a sample size of 20. So if n is 20, that means my degrees of freedom are going to be 19, okay? So I automatically know on my T chart, I'm going to row 19. So I'm somewhere on this row, okay? Let's see what else it says. It also says a 98% confidence interval. Okay, this is where it's tricky because you're missing a formula. Now, you may want to put this here at the bottom of this paper that has your Z chart, but for your T chart area, okay, here's how you find it. You're going to take 0.5 minus your confidence level over 2. That's how you find the area. Now this confidence level has to be a decimal. So you're going to have to change your percent to a decimal. But this is how you find your area. 0.5 minus the confidence level over 2. Okay, so here's my confidence level. So my area for my T-chart is going to be 0.5 minus 0.98, because I made it a decimal, I divided it by 100, over 2. Okay, that's the secret formula. So when I put that in my calculator, I'm going to get 0.01. So this is the column on the T-chart, this is the row on the T-chart. Okay, so I want row 19, because my sample size was 20, so degrees of freedom are 19, and 0.01 is my area, so here's my T, 2.539. And that's your answer, 2.539. Done. Okay, and there you go. All right, now number 4, same thing. We're just going to practice it again. Now the answer in the back for number 4 is wrong, so please ignore that. So we're going to do the correct answer together. Okay, so here's our sample size. It's 25. That means my degrees of freedom is 24. You just have to subtract 1. Okay, now this 90%, that's going to help me with my area. So my area is going to be 0.5 minus 0.90, because I had to divide 90% by 100, divided by 2. Okay, I put that into my calculator and I come out with 0.05. So that's my area. Okay, I'm going to go to my T-chart. Okay, we said degrees of freedom was 24, so here's my row. My area we found was 0.05, that's my column. And then here's my correct T value, 1.711. So that is going to be the answer, 1.711 for number 4. Okay, so that's how you use your T-chart. Now, we're going to come back to the T-chart for other things, and we'll talk about it more then. But for numbers 3 and 4, that's what we're dealing with. Okay? All right. Now, number 5 and number 6 both ask for a sample size. How large a sample? What sample size is needed? So they're both involving sample size. So those are 2 other equations you need to put somewhere, okay? And this deals with chapter 8. So one sample size is going to be z squared times p hat times q hat over e squared. The other sample size is going to be z squared times sigma squared over e squared. Okay, those are your 2 sample size equations. You're going to need both of those, okay? So let's look at the difference. They both have z squareds and e squareds. The way that you tell which one you want is because this one has sigma squared. You can only use this one if you have the population standard deviation. This one has p hat q hat. You can only use this one if you have the sample proportion, okay? So just depending on your information, that's going to pick which one you use. Okay, so let's read number 5. How large a sample should be selected so the margin of error of estimate for a 95% confidence interval for P is this, when the value of the sample proportion obtained from a preliminary sample is 0.30. Okay, so I didn't see anything about sigma or standard deviation, but I did see the phrase sample proportion. So that means I only have one choice in formula, and it's this one, because p hat is my sample proportion. So that's the one that I'm going to use. All right, so we need to make sure we have all these values. So first of all, I need to find z. That's where the 95% comes in. That's where this chart comes in. 95%, these are your Z values for confidence levels. So for chapter 8 only. Okay, so we said 95%, 1.96. That's my Z. Okay, easy enough. All right, now I need a p hat. So I need the sample proportion. Okay, now be careful here. If you just read these three little words right here, it says P is this. Well, first of all, I don't want P. I want P hat. And second of all, P does not equal this. What is this number? Well, you have to read the whole sentence, and the whole sentence is telling you the margin of error of estimate for this is this. So this number is the margin of error. They do this all the time. This is how it's going to be on your test. You're going to have to read the whole sentence. So the margin of error is this number, which is E. Okay, don't be fooled. When the value of the sample proportion, that's P hat, obtained from a preliminary sample is 0.30. So P hat is 0.30. So be really careful with that. Okay, the only other thing I lack now is Q hat. Now remember, they're never ever going to give you Q hat. Q hat is 1 minus P hat. So 1 minus 0.30 is 0.70. So now you have everything you need. So we're ready to put it in. So Z is going to be squared. P hat is not. Q hat is not. E is also squared. Okay, when I put all that in my calculator, I come out with 398.4. Now I need a whole number. Remember what you do with n. You always, always, always round up. Now 398 is going to be an option. 399 will be an option. 400 will be an option. You're going to have to remember you always round up to the next whole number. Okay? All right, number 6. Ish wants to create a 99% confidence interval for the mean of a population whose standard deviation is this. Okay, he wants the margin of error to be this. What sample size is needed? So again, we are back to our two choices on sample size. Well, I didn't see I didn't see sample proportion, but I did hear the phrase standard deviation. So I'm thinking this one. Let's just make sure. All right, so population whose standard deviation is this. Sure enough, we have sigma. That means it's going to have to be this formula. Okay, so let's identify what we have. First, we need Z. Well, when we are doing confidence intervals, Z is going to be right here. Okay, so 99%, 2.58. There's our Z. All right, next we need sigma. We said population standard deviation. That's our sigma. And we need margin of error, 3.1. Okay, now all we have to do is plug it in. Now for this formula, every single item is squared. So make sure you're squaring everything. Okay, I put that in my calculator. I came up with 69.82, but you always round up. And so I came up with 70 for that guy. Okay. All right, let's try the next one. Okay, number 7. Joy and Kirsten want to determine how large a sample. Oh, okay, we're back to here. We have to pick. These are our two sample equations. Should be selected so that the margin of error of the estimate for P is this. So remember, this number is the margin of error with a 99% confidence level and a sample proportion of this. So I never saw standard deviation, but I did see sample proportion. That means we're back to this guy. That's our formula. Okay, so here we go. We want Z. That comes from this. We're going to go right to our Z chart again, just like we did before. And Z is 2.58. Okay, we want a P hat. We identified our sample proportion as 0.68. We need a Q hat. Remember, you're never going to find that in the problem. That's going to be 1 minus P hat, which I guess it would help if I was on the right page on my answer key, 0.32, okay? And then last but not least, we need the margin of error. So remember, sometimes that's tricky to find, but here it is. You have to read it really carefully. All right, we have everything. So Z squared, 2.58 squared. Now remember, P hat is not squared. He's just wearing a hat. Q hat is not squared. He's just wearing a hat. Over E, which is squared. There we go. Now we put that in our calculator. Remember, we want to round up. Round up. And I came up with 2,515. And there we go. Okay. So that helps you practice those sample ones. You're going to have each of those equations. So make sure you're comfortable with both. Okay, next question. Audrey determines that a random sample of 82 customers who visited a department store spent an average of $71 at the store. Suppose the standard deviation of expenditures at this store is sigma equals $19. The 98% confidence interval for the population mean is what? Okay, so to find confidence intervals, you have three choices. You have sigma known, sigma unknown, and P. Well, we have sigma, so we are obviously sigma known. Okay, so let's go back to our little sheet where we're filling some things in. We did sample size already, right? Okay, if we have sigma known, these are for confidence intervals, okay, sigma known, you're going to do X bar plus or minus E. Now, E is going to be Z times sigma over the square root of N. That's it. That's how you find a confidence interval for sigma known. Okay, let's identify what we have so far. All right, a random sample of 82, that's your N, who visited the department store spent an average of 71. That's your X bar. You have to be able to identify these. Okay, then we have sigma. That's how we knew it was sigma known. And this percent confidence interval, because it's sigma known, is from here. Now, this chart is only for sigma known and proportions. That's it. And it deals with chapter 8 with confidence levels. Okay, that's what this chart is for. So we were dealing with 98%. That is 2.33. Okay, now we've identified everything. Okay, now we're going to use this formula. So first thing we need to find is E, which is this. Okay, so E is Z times sigma over the square root of N. Okay, put that in my calculator and I come up with 4.89. All right, then I take X bar minus that and X bar plus that, and that gives me my interval. So I'm gonna have 71, that's my X bar, minus 4.89, and 71 plus 4.89. I put those values in parentheses, and there they are. 66.11 is the lower, and 75.89 is the higher. And this is my interval. And you just put a little comma right in between. And there's your answer. Okay? All right, let's look at number 9. So Abigail Whitlock found out that the mean IQ score for a sample of 61 students, okay, there's our N, selected from a high school is 87. All right, you may need to go back and read that again. What she found is the mean is 87. That's X bar. Sometimes these things are hidden. Suppose the standard deviation of IQs at this school is sigma equals 8.4. Okay, so this was sigma known because it gave us sigma. This one is also sigma known because it gives us sigma. The 99% confidence interval for the population mean is what? Okay, so confidence intervals, that's what we're doing down here. For sigma known, we have our formula, okay? It said we were dealing with a 99% interval, that's 2.58. We're gonna find E, so that's just Z times sigma divided by the square root of N, okay? Put that in my calculator and I came up with 2.77. Now I'm gonna take X bar minus that value and X bar plus that value. That's my interval. So 84.23, 89.77. And there we go, okay? So not hard, okay? So again, I just kind of wrote down some things I needed to remember right here. So far, that's all we've used. All right, let's try this one down at the bottom. So we have Jake. Jake found out that a random sample of 1,100 adults, okay, there's our N, that of this sample, okay, 32% of them are smokers. So I've got a percent. Based on this sample, the 90% confidence interval of the true proportion of all adults who are smokers is what? Okay, so we are no longer sigma known. Now we are proportions, or P, okay? So instead of X bar plus or minus E, we're gonna be P hat plus or minus E. That's what we are instead, okay? So what is our E then? Okay, our E is a little different. It's still Z, but now it's times this big giant square root of P hat times Q hat over N, okay? That's now what we are. This is for proportion. Anytime you see P, we still get to use this, okay? All right, so here we go. This sample showed this percent. So this percent is in the same sentence as the sample. This means this is the sample proportion. This is P hat. You have to turn it into a decimal though, okay? P hat is the sample proportion. It's in the same sentence as the sample, so that's our P hat. Now again, we're also gonna need Q hat for these formulas. So you're gonna have to be able to do 1 minus 3.2. That gives us 0.68, okay? And then the last thing we're gonna need is Z, 90% confidence interval. Remember, this is good for sigma known and proportions. Okay, so we read it right off of here, and it's 1.65. Okay. All right, now we're ready for our formula. So here we go. We're gonna do this portion to find E, and then we're gonna do P hat plus or minus it, and that gives us our interval. Okay, so E equals Z times this big giant square root of P hat times Q hat over N. Now, some of you don't like to do all this at once. It's a little much for you in your calculator. You don't have to. You can take it 2 steps at a time. You can take this one and then, or I mean 1 step at a time. You can take this and find this answer and then multiply it by 1.65. But when you find E, it's 0.023. Okay, Now I'm going to take p hat, which is 0.32, minus 0.023, and I'm going to take p hat plus 0.023. And that's going to give me my interval. I'm kind of running out of room over here. I'll stick it down here. So I've got an interval of 0.297 is my lower and 0.343 is my upper. Okay, and there's my interval. Okay, so we've covered proportions. I'm just going to call this P, and 2 sigma knowns. Okay, all right, for our confidence interval. All right, let's see what's going on over here. This is the last page of chapter 8. This finishes up chapter 8, and then the rest of the test is on chapter 9. Okay, so number 11, a grocery store is interested in how many customers purchase gallons of milk. Jillian randomly selects 300 customers. All right, that's our N. And finds that 230 of them purchase milk. Ooh, that's weird. Okay. We'll come back. Use a 95% confidence interval to estimate the true proportion of customers that buy gallons of milk. Well, it's got to be a proportion problem, right? Because it mentions the word proportion. But I don't have a p hat. A p hat is always a decimal. Proportions are always decimals. I have the sample size, and then I know out of this sample, this many purchased milk. So the way you find p hat is you take that smaller number divided by the sample size, and that is going to give you your decimal. That's your p hat. So that's a really tricky problem. The larger numbers you're in, your p hat is the smaller divided by the larger. Okay? And then of course you need a q hat, so 1 minus 0.77 is 0.23. Okay, and then this 95%, we just go to our Z chart and it's 1.96. All right, so we're still dealing with proportion. We got our Z from here. So now we're gonna find E, our margin of error, and we're gonna do p hat plus or minus it. Okay, so here's E. I'm going to do Z times this great big square root of 0.77 times 0.23 over 300. Okay, that's going to give me a margin of error of 0.048. So I'm going to take p hat minus this, and I'm going to take p hat plus this. That's going to give me a confidence interval of 0.722 to 0.818. And there's my interval. Okay. All right, let's try number 12. Okay, so number 12 says we have a random sample of 765 persons. There's our N. Showed that 13.5% do not have any health insurance. Okay, the minute I see percent there, and you can continue on and see the word proportion, we have one more P problem. We have another proportion interval. So remember, if it's in the same sentence as the sample, this percent is your P hat. You just need to turn it into a decimal. That's all. That's also going to give you your Q hat, which is 0.865. Okay. Here's our Z. We just go to our Z chart for 95%. We get 1.96. Okay. And then we're ready for our formulas. So we're going to find the margin of error. It's going to be Z times the great big square root, 0.135. Times 0.865 all over 765, because that's our N. Okay, did I go off the page a little bit? Okay. All right, so that's going to give us a margin of error of 0.0242. Okay, now I'm going to take p hat minus this number, and I'm going to take p hat plus this number, okay? And I don't really have any more room, but my confidence interval is gonna be 0.111, comma, 0.159. There's my interval. All right, so if you've noticed, we have already covered sigma known and we've covered proportion, but we have not covered sigma unknown. That is this guy down here. This is the only sigma unknown confidence interval you're gonna have. This is it. It's gonna be really obvious because it's just a line of numbers. It's just 10 observations in a line, and the only data it gives you is the confidence interval, and that's it. So this is sigma unknown. Okay, this is sigma unknown. So let's talk about him and put his formulas on our paper, and then we'll jump right in, okay? Because that's the only kind that you're going to have on your test is the one just like that I showed you. Okay, so sigma unknown, all right, is still gonna be X bar plus or minus E, just like sigma known. But we no longer have Z. We have T. So this is when the T chart has to come into play. We have T, okay? Then you're gonna take T times S over square root of N, okay? So we don't have sigma, we have the sample standard deviation, not the population standard deviation. So we cannot use the Z chart, we have to use the T table. And we don't have sigma, we have S instead. So that's the difference, okay? For your sigma unknown problem, you don't have any information. The only thing you have is N. You don't have X bar and you don't have S. That's the problem. So you are going to have to put these numbers into your calculator in a list, and you're going to have to go from there, okay? So let's make sure we know how to do that. Let's go over here, okay? You're going to need to use stat edit. Okay, can you see that all right? Okay, stat edit. And you're going to have to make a list in L1. Okay, so let's do that. Okay, here we go. Here's my calculator. I'm gonna go to stat edit. Okay, I already have something up here, so I'm gonna clear it out. All right, I'm gonna put all the values into this list. So 12, 18, whoops, 23, 20, 24, 17, 22, 25, 21, 19. So I put them all in that list, okay? And then I'm gonna quit, second mode, okay? So I put them all in that list, and then I'm gonna quit, which is second mode. Then I'm gonna go back to stat, and I'm gonna scoot over until I get to calc. And then at calc, I'm gonna use one var stats, okay? I'm gonna use one var stats. Now, all I need is L1. That's all I need, L1 only. This gives me X bar and S. Because remember, I need X bar and S for my formulas. So I'm doing all this to get X bar and S, okay? So I'm gonna go back to my calculator. I already quit. I'm gonna do stat. I'm gonna scoot over to calc. Here's one var stats, okay? I only want L1. I don't want anything else. And there we go, okay? This is my X bar, 20.1. So I'm gonna come over here and put X bar equals 20.1. I'm only trying to get two pieces of information. I'm trying to get X bar and I'm trying to get S. Now you're gonna see SX. That's okay, that's what you want, okay? Your calculator's gonna say SX, but it's really S. So 3.8427. I always like to take it out 4 places when I'm getting it from the calculator. Once you have that information, you're done. Okay, that's all you needed. So in your calculator, it says SX in calculator, right? But it's just S. That's what we wanted. Okay, perfect. So now that I have that information, the only other thing I need to find is T. So that comes from my T chart. Okay, I have to find T. Well, to find T, I need the degrees of freedom. So N is 10, N minus 1 is 9. Okay, now in addition to degrees of freedom for the T chart, I also need the area for the T chart. Okay, so remember, here's how we find the area for the T chart is right here. So I'm going to do 0.5 minus, here's my confidence level, 0.98, because I had to make it a decimal, over 2. Okay, that's going to give me 0.01. Okay, so my T, using this information, okay, go to my T chart. I went to 9 degrees of freedom, 0.01. I go down 2.821. That's the T that I want to use. Okay. So my T is 2.821. Whew. Okay, that was a lot of work. This problem is a lot of work. So here we go. I have X bar. I got it from my calculator. I'm just about to calculate E. I found T from my T chart. S came from my calculator, and there were 10 values. So I finally have all the information I need to do my formula. Okay, so my margin of error is going to be T times S divided by the square root of N. That gives me a margin of error of 3.4821. Okay, 3.4821. Then I'm going to take X bar, which came from my calculator, minus this margin of error, and plus this margin of error. And I finally get my confidence interval right here. And there it is, 16.7 to 23.53. So that is your only sigma unknown. You will need to use 1-bar stats in your calculator, so be sure you remember how to do that and find all this information, okay? And just use this little formula sheet, you know, kind of make one like this for yourself to help you get to it. That is everything for chapter 8 that you're gonna need to know, okay? So we will start then chapter 9 on the next page, which is 14. Okay, starts with number 14. So this page is just a quick little page to remind you about chapter 9 and how we deal with things. So this paper is now done. This is only good for chapter 8 for confidence levels and confidence intervals. Okay, you still need the T chart, still need this. But now we also need this. This is where this comes in, chapter 9. Okay, so the null hypothesis. What is the null hypothesis a claim about? Here's the important part. It is a population parameter. Because remember, the null hypothesis deals with mu and p. That's the population mean and the population proportion. So it's a population parameter. That's really important. Where the claim, can you still see that? Yeah, where the claim is true until declared false. Okay, population parameter where the claim is true until declared false. That is the definition of a null. Okay. All right, 15 and 16 wants to talk about type 1 and type 2 errors. When do they occur? What exactly do they mean? Okay, a type 1 error is when a true null is rejected. That's a type 1 error. A type 2 error is when a false null is not rejected. So if you remember, we kind of talked about it like in terms of the law. So this would be an innocent man goes to jail. This would be a guilty man goes free. So I don't know if that helps, or if that just confuses you, just learn this. Type 1, a true null is rejected. A false null is not rejected. Okay, those are the two errors. All right, number 17. In a hypothesis test, the probability of committing a type 1 error is called what? Well, that's actually right on your little cheat sheet. Look at here. The probability of making a type 1 error is the significance level. It's the same as alpha. Okay, so this is the significance level, or alpha. Okay. All right, so 18, 19, 20, 21 is a repeat. I'm sorry. It's exactly the same as number 18, so you don't have to do that one. But for 18, 19, 20, right on your little cheat sheet, it wants you to look at the alternative hypothesis and tell what kind of inequality sign is used in each of these tests. So in a left-tailed hypothesis, the sign in the alternative is less than. The point points to the left, okay? In a right-tailed hypothesis, the sign for the alternative is greater than. The point points to the right, okay? What about a two-tailed? Okay, remember that's just not equal to. That's what we're looking at for that one. And then 21's a repeat, so we don't need it. Okay, here we go. These want you to just write the null and the alternative for each of these, just to make sure that you're comfortable identifying these. So Araceli wants to test if the mean price of houses in an area is greater than 145,000. What are the null and alternative hypotheses? Okay, so the null is always going to be equal to whatever number you see, okay? Equal to this, whatever you see, it's gonna be equal. The alternative is when you have to think about what kind of test. So greater than would be a greater than sign. That would be a right-tailed test. There you go. Okay, let's look at 23. Giselle wants to test if the mean annual salary of all lawyers in a city is different than 110,000. What are the null and the alternative hypotheses? Okay, so the null we know is going to be equal to whatever value we see. The alternative is the one we have to think about. So this doesn't say greater than, it doesn't say less than, it says different. Different from is a two-tailed test. Okay, if you see the words different from or changed, either one of those, you may want to write those on here, okay? Different from or changed, different or changed. That's a two-tailed test, okay? All right, Jaden, poor Jaden, his name got spelled wrong. Dang, autocorrect, okay. Jaden wants to test if elementary school children spend less than 30 minutes per day on homework. What are the null and the alternative? Okay, so we know the null is going to be equal to the number we see. The alternative, this is less than, so must be a left-tailed test. And there we go. Okay. All right, one more of these. It's number 25. Okay, Jackie and her calculators. Here we go. A calculator company has changed the electronics in its calculators. Previously, the calculator has had a mean lifespan of 6 years. Jackie wants to perform a hypothesis test to determine whether the mean lifespan has changed. What are the null and alternative hypotheses? Okay, so null is going to be equal to the number. Alternative, again, if it says different or changed, it's a two-tailed test. Okay, and there you go. All right. Okay, so number 26 wants to know whether you think you should fail to reject or reject the hypothesis. Okay, so this tells you that you have a two-tailed hypothesis test with a significance level of 0.025. Significance level means alpha. So this is what it's telling you. There's your alpha. It's also telling you that it calculated a p-value of 0.4. What conclusion can be drawn? Well, that's in your cheat sheet. Okay, so it doesn't matter whether you're doing sigma's known, sigma unknown, or proportion. It really doesn't matter. Here's what it boils down to. If you just pick a page. If alpha is greater than the p-value, reject. If alpha is less than the p-value, fail to reject. That's the rule. So here's alpha, here's the p-value. Alpha is, in this case, less than the p-value. So according to our rule, what are we going to do? We are going to fail to reject. And there we go. That's all you got to do. You just got to compare them and figure out which, if the alpha is bigger or smaller. And there you go. Okay. All right, number 27. In a hypothesis test for a population mean where sigma is known, okay, the test statistic for the sample size of 55, that's in, was calculated to be negative 2.14. Okay, let's stop there. What in the heck is a test statistic? Because we have not heard that at all. Well, surprise. So they sent the final over and they are using the phrase test statistic, but that means the observed value. So anytime you see Z observed or T observed, that is the test statistic, okay? So since sigma is known, that is going to be Z observed. That's our test statistic, okay? Find the p-value of a one-tailed hypothesis test. Okay, so we're going to find the page sigma is known, okay? You may want to write test statistic by your Z observed, okay? All right, here's how you find the p-value. It's number 2. This is your p-value. Now, we don't have to worry about multiplying the answer by 2 because it's not a two-tailed test. So we can either use the right-tailed test or the left-tailed test because it doesn't tell us which to use, right? It just tells us sigma is known, okay? So let's think about this a minute. It actually does tell us. Would this value be for a left-tailed test or a right-tailed test? It's negative. Think about where that would fall in your curve. This would be a left-tailed test. Okay, that's one of those things you just are going to have to be aware of, okay? So we're going to do left-tailed test. We're going to have this formula right here in our normal CDF. That's going to give you the p-value. To find your p-value, we do normal CDF. That's how you find your p-value, okay? For a left-tailed test, right on here under sigma's known, we're gonna have negative infinity as our lower bound. This test statistic is our upper bound, comma 0, comma 1. I don't know why I squished that in there like that, sorry. But if you put that in your calculator, you're going to come up with 0.0162. That is your p-value, Okay, that is your p-value. So sigma known, I turn to that page. Test statistic is z observed. Find the p-value. It's a one-tailed test. Which tail is it? It's going to be left-tailed because z observed is negative. Normal CDF is how you find a p-value. Put in your values. There's your p-value. Okay. Now, when is the t distribution used? When is the only time we ever mess with t? Well, there's only 3 instances: sigma known, proportion, or sigma unknown. And the only time we ever deal with t is sigma unknown. Okay, so just kind of make sure you remember that little guy. All right, the very last time we have to find a p-value is number 29. Okay, we want to deal with a p-value again. So in a test of hypothesis for a population mean where sigma is unknown, okay, so we're going to turn to our sigma unknown. Remember, this is our test statistic, by the way, t observed if we need to know it. Callie and Abby determined the test statistic for the sample size of 64 was calculated to be 3.257. So that was the test statistic. That was t observed. Okay. All right, that's what we found. All right, find the p-value for this hypothesis test. So notice we had to find 2 p-values, one for sigma known, one for sigma unknown. Okay. All right, so here we go. Sigma unknown, here's how you find p-values. Now remember, when sigma's unknown, your p-values are a range. They're a range. Now, we're not going to have to worry about multiplying these by 2 or anything like that, okay, because this is fine. It doesn't, if we look at this, it's not a two-tailed test. What kind of test is this? If it's positive, this is a right-tailed test. I should have put on here that it was a one-tailed test. Sorry about that. Okay, so it's going to be a range. Here's how we do it. Using the degrees of freedom, find the correct row on the t-chart. Okay, so we need degrees of freedom. 64 minus 1 is 63. Okay. Locate the 2 t-values that your t observed falls between. Okay, so I had to turn here to the back to get to these 60s, right? And I'm on 63, row 63, okay? Now, it told me to find where my t observed fell between, okay? My t observed, my test statistic is 3.257. So when I look, it doesn't fall between any of these. It's like way out here. It's like 3.257 is like way the heck out here on the end. You can't even see it because I don't even have it in. Sorry, guys. Let me scooch you over a little bit. Now you see it. Okay. All right, so 3.257, okay? So way out here. So what is the range of values? These are your p-values. You go straight up, okay? So 0.001 to 0. That is what we're dealing with. These are your p-values. If this had fallen between these two, those would be my p-values. It fell over here, so these are my p-values, okay? So I'm going to then write here that my p-values, you always want to do the smallest one first, and then the bigger one looks like this. That's my p-value range. It's only a range because it's sigma unknown. Now, this is probably not going to be on a choice. They usually don't like to use the value of 0, so it will probably just look like this, or it may look like this, okay? It will probably look like one of these. So it's just going to be up to you to realize yours is also going to be hanging off the end of the test, hanging off the end of the chart. So you're going to have one that's way out here. And what you're going to have to remember is it probably won't include 0. It's probably just going to have this guy here. And then you're going to have to remember that the p-value is smaller than that, okay? Or that that's greater than the p-value, depending on how they write it, just so that you're aware. So that one's kind of tricky. Okay, now we get into true hypothesis testing. But you do not have to do the p-value approach. All of your hypothesis tests are only going to be critical value approach. That's it, which is great news because it's so much simpler and it's faster and it's visual. So you can draw your test and look at it, okay? All right, so let's do these last few to practice this critical value approach only. So you're gonna have to think of, is it sigma known, sigma unknown, or proportion? So that's important. You're gonna have to figure out that. And then you're also gonna have to figure out, is it left-tailed, right-tailed, or two-tailed? Okay, so here we go. A company that manufactures ceiling fans claims that the fans last an average of 5,500 hours. That's the claim. That is your null. Okay, that's what they're claiming. Now, Lisbeth is fascinated and wants to test this hypothesis that the mean life of the fans is less than. So Lisbeth is convinced they're less than. That is your alternative. And less than means, whoops, a left-tailed test. So that is what you're dealing with, is a left-tailed test, okay? So you could go ahead and draw your test. Here's your left-tailed test. This is your fail to reject area. Here's your critical value. Now, I would expect my critical value to be negative because it's a left-tailed test, right? So keep that in mind. This critical value should be negative. Okay, let's keep reading. A sample of 48 fans, there's my N, gave a mean life of 5,200 hours. There's my X bar. With a standard deviation of 100. Okay, be careful now. Students see standard deviation and they want to say sigma. This is not sigma. How do I know it's not? Because it's in the same sentence as sample. This is the number, the sample. This is the sample mean. This is the sample standard deviation. That guy is S. This is a sigma unknown problem, okay? This is sigma unknown. You're gonna have to be able to recognize that this is S. Okay, the significance level of the hypothesis test is 2.5%. That's your alpha. I'm gonna turn it into a decimal by dividing by 100. That alpha is also the area under the curve that's shaded. All right, so here we go. Now we just want to follow our steps. So we're going to go to sigma unknown. We don't care about the p-value approach. We're only doing critical value approach, okay? So first thing we're going to do is find t observed from this formula. Remember, this is also the test statistic. So we're going to have x bar minus mu divided by s over square root of n, because this is the same thing as s over square root of n. Okay, so t observed, that's our test statistic, is going to be x bar minus mu. Remember, mu is in your null, divided by s over square root of n. Okay, my pencil does not want to stay straight. Okay, and what did I get when I did this? Let's see, I came up with negative 20.785. Okay, so remember, that is my test statistic. That's my t observed is my test statistic. Okay, so I found t observed. I get to check that off. Find t critical from the t-chart. using alpha as the area, and then using degrees of freedom. Okay, so that crazy formula that we came up with for the area, right? This formula up here, we don't have to deal with that anymore with chapter 9. That's not something we have to deal with remember, it was only in the beginning when we were starting to deal with the T-chart for chapter 8. Okay, so here we go. I'm going to my T-chart. It told me that my N was 48, so I'm actually going to have to turn it over and find degrees of freedom 47 to get my row, right? Okay, so 48 minus 1 is 47. Now my alpha, remember I wrote down my alpha was 0.025. That gives you your area. And then there you go. There's your T, 2.012. Everybody see that? So alpha, degrees of freedom. Okay. So T critical was 2.012. Now we have to stop and talk about this a minute. Every value on that T chart, every value is positive. Should your critical value, which is what goes right here, should it be positive for a left-tailed test? No, it should be negative. So you're going to make it negative because it's a left-tailed test. Okay. Now it's going to let you're going to have the positive version and the negative version on your test. Make sure you choose the negative. Okay. Pay close attention to that. Okay. Now it wants the result of the test. This means, do we reject or fail to reject? Now this is going to be multiple choice. So you're actually going to have 3 options. You're only going to have A, B, and C for this question. A would be reject. B would be fail to reject. And then your other option for C would be that you don't have enough information. Don't pick that. You always have enough information. Okay, these are your only choices. So if this is my critical value, where does my test statistic fall? Way over here, right? In the negatives, negative 20.785. That's definitely the rejection region. So your result is you're going to reject the null. That's what you're going to write, reject the null, or choose that. Okay. All right, let's move on to 31. Okay, 31 says, Dr. Trejo asks the patient to check his heart rate each day. The patient has 20 readings with an average of 85 beats per minute. Okay, this is your sample, is the 20. And the average is your sample mean, so your X bar of 85. Now, Dr. Trejo says that 5 years ago, you never have to worry about time in these problems. The heart rate was 81. Okay, so that is actually going to be your null. Okay, that's what it was. That was the average. That was the 81. Okay, given a 2.5 significance level, that's our alpha, change it to a decimal, and the fact that all people similar to the patient have a 7 beats per minute standard deviation. Okay, so what is that? We know it's a standard deviation. Is it population or is it sample? Well, this says all people. That means we have a sigma. This is sigma known, okay? And there's our sigma, okay? Is there a reason to believe that the heart rate is different than it was 5 years ago? So what is our alternative hypothesis? Two-tailed. Everybody see that? Two-tailed. Because if we see the words different or changed, it's a two-tailed. So when you find the heart rate problem on your test, it's two-tailed, sigma known. That's what you're dealing with, okay? All right, so now we're going to follow the directions. We're going to turn to sigma known. We're not worried about p-value. We're on critical value approach only. We're going to take z observed from the formula. That's our test statistic. We're going to do x bar minus mu divided by sigma over the square root of n. Okay, so z observed, that's our test statistic, is going to be x bar minus mu, that came from the null, divided by sigma over square root of n. Okay, that gives us 2.56. That is our test statistic, 2.56. Okay, we didn't draw our picture, so let's draw a picture. Now, a two-tailed test means we have two critical values. We're going to have a negative critical value and a positive critical value. This is our fail to reject region. Okay, all right. Now we need the critical value, okay? Now, remember, this alpha is this shaded region, but there's two regions. So we're actually going to take our alpha and divide it by 2, so that when we do that, we get 0.0125. That's what we're dealing with for our alpha. We had to divide by 2 because it was a two-tailed region. Okay, sigma known. Let's find out how to find z critical. To find z critical, we use inverse norm. Alpha, 0, 1. But look, if it's a two-tailed test, what did we have to do? Divide alpha by 2 first. That's what we did here. So to find z critical, we're going to take inverse norm. We divided alpha by 2, and we got 0.0125. Comma 0, comma 1. We're going to put that in our calculator. This is because it was a two-tailed test. And we come up with negative 2.24. Okay. Now, that takes into account this critical value, but we need another one. We need a positive critical value. So you're also going to have the positive version. So make sure you choose the answer that has both, right? Because it's a two-tailed test. Now, the result of the test, here we go. We're looking at 2.56. So where would 2.56 fall? Somewhere over in here, right? So we are still going to reject the null. Okay, because it falls into the shaded region. The shaded region is the rejection region. Okay. All right. Moving along here. Let's see what Daisy's doing. Okay. Daisy claims that more than 12% of the students in her school do not have reliable internet access at home. Okay, the minute you see percents, this is a proportion. This is a P, okay? All right, so here's what we're gonna find out. She claims that more than, that's what she's claiming, okay? That means the null, well, first of all, the null and the alternative is gonna involve P instead of mu for a proportion. Okay, she's claiming that more than, well, you know the null has to be equal to. So it has to be equal to this 12% that we're going to turn into a decimal. Daisy's claiming more than. That means greater than. That's what she wants to test. And that means a right-tailed test. Okay? So that's what this is, a right-tailed test. Okay? And this is our failed to reject area. We're going to have one critical value. And because it's a right-tailed test, our critical value is going to be positive. So these are things you need to think about. Okay, so Daisy's worried. To test this claim, she sampled 300 students. Okay, 22% of the students in her sample. So this percent relates to the sample. That means that is P hat. the sample proportion. Make it into a decimal. That many did not have reliable access at home. The significance level, that's our alpha, is 1.5%. So you're going to need to make him a decimal. Okay, there we go. Now, we're going to turn our little cheat sheet paper over to proportion. Here we go. We're not interested in p-value, only critical value. So z observed, test statistic, we're doing this. P hat minus p, that's from the null, divided by this, okay? All right, notice what else is in here, q. So I'm going to take p, which is just from my null, 1 minus p, I'm going to need q. So I'm going to have to find that before I do this formula. Okay, so p is 0.12, q is 1 minus 0.12, which is 0.88. So I'm going to have to make sure that I use that. Okay, test statistic is z observed. I'm going to do p hat minus p all over square root of p times q over n. Okay, so you may want to do this in several steps, but I just kind of wanted to throw it all out there to show you what's happening. You may want to do the denominator and come up with a value and then throw that in. You should end up getting 5.33 for that. Okay, that's your test statistic. So make sure you put that in, z observed. Okay, now for z critical, inverse norm. Now we do not have a two-tailed test, so we don't have to divide alpha by anything. We just get to throw alpha right in, okay? So z critical is going to be inverse norm alpha, which we said was 0.015, comma 0, comma 1, and it came up with negative 2.17. Okay, so we got to think again. Should this be negative? No, it's a right-tailed test. So make it positive, okay? 2.17. All right, we did it. Okay, now if we're comparing here, 5.33 is going to fall over here, okay, in this area, which means, again, we are going to reject the null. I'll tell you, we end up rejecting them for everything on this test. I'm so sorry. It was a horrible coincidence. You will not have every one of them be reject on the test. Okay, 3 more. Here we go, 33. All right, on a stretch of highway where a posted speed limit is 75 miles per hour, data collected 5 years ago, again, we don't care about time, indicated that the average speed of vehicles was actually 73 miles per hour. Okay, let me save you some time on this problem. Don't worry about the speed limit sign, the posted speed limit. Okay, so you're going to have this question on your test. Ignore the time and ignore the posted speed limit. It's not important. What's important is this average speed of vehicles. This is your mu. This is your null. Okay, so ignore the posted, ignore the time. That speed that you see is going to be your mu. Okay, Laney and Jordan recently found out that a sample, that's 35 vehicles, were traveling an average speed of 76. Okay, that's X bar. It's talking about the sample. They would like to know whether the average speed of vehicles is now different. What kind of test is that? That's our two-tailed from 73. It is known that the population standard deviation is equal to 5. That is sigma. So we're back to sigma known, okay? And your significance level is 0.01 because we're dividing that by 100. Okay, so notice that for both sigma known problems, we have had a two-tailed test. Keep that in mind. That's going to be your situation on your test. Your actual hypothesis testing, sigma known is going to be two-tailed, okay? All right, so we know we're going to have two-tailed, okay? That means we're going to have two critical values. We're going to have a negative and a positive. This is our fail to reject area. These are our rejection regions. Now, since we have two shaded areas, we're going to have to divide alpha by 2. And that turns into 0.005 for each of these. Okay, our test statistic is Z observed. Okay, so if we turn back to sigma known, we're going to use this. Our denominator is going to be sigma over square root of n. Okay, so we're going to have x bar minus mu, that came from the null, over sigma divided by the square root of n. And this gives us 3.55. That is our test statistic. Okay, now we need our Z critical values. Remember, there's going to be 2. To find Z critical, you use inverse norm. Okay, so it's a two-tailed test. We have to divide alpha by 2. We already did that. We're going to put that in here with a 0 and a 1. Okay, so we're going to use 0.005, comma 0, comma 1, and that gave me negative 2.58. But we are also going to use positive 2.58. So here's negative 2.58. Here's positive 2.58. Okay, and now we just do our test. Okay, so 3.55 is going to fall over here, surprise, surprise, sorry, in our shaded region, which is our reject the null area, our rejection region. Okay, so sigma known is two-tailed test. Okay, let's see what we have here. We have Raquel and Liberty. They're testing the life of 40 batteries. Oh, there's our N. And found them to last an average of 1,500 hours. Okay, that's talking about the 40 batteries, so that's X bar, with a standard deviation of 100 hours. Still in the same sentence, talking about the 40 batteries, so that is the sample standard deviation. That's our S. So sigma is unknown. Okay, all right. The company claims they last 1,600 hours on average. Okay, that's our null. Okay, using a significance level of 5%, that's our alpha divided by 100. Do the ladies have enough evidence to claim these batteries have a shorter lifespan than the manufacturer claims they do? Well, shorter would be less than. That's our test. We have a left tail test. Okay, now I don't know if you remember, but our other sigma unknown was also left-tailed test. Okay, so sigma known, two-tailed. Sigma unknown, left-tailed. That means your proportion tests are going to be right-tailed. Okay, all right, now because this is left-tailed, you expect your critical value to be what? Negative. Okay, keep that in mind. This is your fail to reject. Here's your alpha. You don't have to do anything with it because there's only one little rejection region. Okay, we're going to turn to sigma unknown. We need T observed. That's our test statistic. That's our first step. X bar minus mu divided by S over square root of n. Okay, T observed, that's our test statistic. X bar minus mu divided by S over square root of n. Okay, and let's see, that gave me negative 6.325. Okay, negative 6.325. That's my t observed. Okay, t critical. Okay, t critical is from the t-chart. Alpha is your area using degrees of freedom. We do not have to divide it by 2 because we do not have a two-tailed test. Okay, so here we go. Our alpha is 0.05. Our n is 40, so our degrees of freedom are going to be 39. So way up here at the top of that back page. 39 degrees of freedom, 0.05 for alpha. Our t value is 1.685. 1.685. But remember what we said about the sign, negative, because it is a left tail test. Okay. There we go. All right, now we just have to test it. Here we go. Where would negative 6.325 fall? Way over here. Again, we're rejecting. Sorry, guys. Okay. Okay, we're getting there. Last problem, and we're done. Very last one. Now, again, we had 2 sigma knowns, 2 sigma unknowns, so we would, guess this would be proportion. This would be our second one, but let's see. So Joseph loves animals. He finds out that only 20% of his community is interested in building a new animal shelter. All right, let's stop right there. First of all, nobody ever even sees this number. Why? Because it's written as a word, and by the time you guys get to this, your brains are fried and you're not even reading anymore. So this number you see here, okay, this is your P, all right, because this is a proportion problem. So this is the null. P is 0.20, okay, but you're going to have to turn it into a percent. He asks 300 citizens, so that's our N, whether they are for or against the new shelter. He finds that 30% of the citizens, so 30% of the sample, that means that is P hat. And don't just take 30, just because they put the percent as a word. You've got to remember this is still 30% and you have to turn it into a decimal. Are interested in building the shelter. If he uses a 2% significance level, make sure that's 0.02, can he safely conclude that the actual number of people interested in building the shelter is higher than 20%? That's a greater than. That is a right-tailed test, okay? So your proportion problems are going to be right-tailed tests. Make sure you read this problem. Make sure that you change things to decimals, okay? It's going to be just like this with the percent written out, the numbers written out, so really pay close attention. All right, you have a critical value over here on the right side. Would you expect a positive or negative critical value? Better be positive, right? Okay, now we're doing proportion, so we turn to the proportion cheat sheet. There we go. We're not interested in p-value approach. Calculate z observed. So there's our test statistic. We're going to do p hat minus p, that's from the null, divided by this big square root, which is p, that's from the null, times q, we better find that, over n. Okay, so if our p is 0.2, our q is 0.8, because it's 1 minus p. Okay, so here we go. Z observed, that's the test statistic, is going to be p hat minus p divided by this big old square root of p times q over n. Okay, and we end up with a z observed of 4.33. That's the test statistic. Okay, now we need z critical. Okay, remember z critical is inverse norm. Alpha is your area. We do not need to divide it by 2 because it's not a two-tailed test. So inverse norm, okay. Alpha was 0.02, that's what we need to put in for alpha, comma 0, comma 1. We come up with negative 2.05. Should this value be negative? No, because it's a right-tailed test, okay? So your critical value is 2.05. Where does 4.33 fall? In the reject. Okay, so again, yours will not all be reject, but that's your test, okay? Literally, that is your test. The speed limit problem, the animal shelter, the heart rates, this is your test. Make sure that you study these, study so that you can identify them really quickly and clearly. And then please email me or text me if you have any issues at all. But that is everything you need to know to make 100 on test 4. Don't forget, Wiley is open until this Friday, the 4th at midnight, and then it shuts down. So make sure that you do your Wiley. And then also remember, if Friday doesn't work for you for the test, you can always come in Monday the 7th during 5th hour, and I'll be here Monday the 7th. So good luck, and I will see you guys soon.